Thermogravimetric Analysis, TGA. Principles, instrumentation, data interpretation, and applications in materials characterization. Thermogravimetric Analysis, TGA, is one of the most important and widely used thermal analysis techniques in materials science, chemistry, polymer engineering, nanotechnology, and industrial quality control. The technique measures changes in the mass of a material as a function of temperature and or time, while the sample is subjected to a carefully controlled thermal program and gaseous environment. By monitoring weight loss, weight gain, or weight stability during heating, cooling, or isothermal holding, TGA provides valuable information regarding thermal stability, composition, decomposition mechanisms, moisture content, oxidation behavior, and reaction kinetics. Since its introduction in the early 20th century, TGA has evolved into an indispensable analytical tool for studying polymers, plastics, composites, pharmaceuticals, catalysts, fuels, biomass, ceramics, minerals, and nanomaterials. The technique is particularly powerful because many thermal processes involve the evolution or uptake of gaseous species, resulting in measurable changes in sample mass that directly reflect underlying physical and chemical transformations. Principle of Thermogravimetric Analysis. The fundamental principle of TGA is based on continuously measuring the mass of a sample while it is exposed to a precisely controlled temperature program within a defined atmosphere. As temperature changes, the sample may undergo dehydration, desolvation, evaporation, sublimation, thermal decomposition, oxidation, reduction, pyrolysis, or combustion. Any process that produces or consumes gaseous species results in a measurable change in sample mass. The primary output of a TGA experiment is a thermogram, which typically displays mass percentage as a function of temperature or time. In many cases, the first derivative of the mass loss curve, known as the derivative thermogravimetric (DTG) curve, is also generated. DTG curves improve resolution by clearly identifying the temperatures at which the maximum rates of decomposition occur and help distinguish overlapping thermal events. TGA experiments can be conducted in several modes. Dynamic TGA is the most common approach and involves heating the sample at a constant rate while continuously recording mass changes. Isothermal or static TGA maintains the sample at a fixed temperature while monitoring mass as a function of time, making it useful for studying thermal stability under service conditions. Quasi-static TGA employs a stepwise heating program in which the sample is heated to a selected temperature and held until the mass stabilizes before proceeding to the next temperature interval. This approach often improves separation of overlapping decomposition processes. Instrumentation of a TGA system. A modern TGA instrument consists of a highly sensitive microbalance, a programmable furnace, a gas delivery system, and sophisticated data acquisition software. The microbalance is the heart of the instrument and is capable of detecting extremely small mass changes, often in the microgram range. To ensure accuracy, the balance is carefully isolated from vibration, buoyancy effects, and thermal disturbances generated by the furnace. The furnace provides a controlled thermal environment and can typically operate from ambient temperature to 1,000 to 1,600 degrees Celsius, depending on instrument design. Precise control of heating rates, cooling rates, and temperature holds allows researchers to simulate a wide range of processing and service conditions. A gas delivery system equipped with mass flow controllers regulates the atmosphere surrounding the sample. The atmosphere may be inert, oxidizing, reducing, or reactive, depending on the experimental objectives. Modern instruments allow automated switching between different gases during a run, enabling complex analyses such as determination of polymer content, carbon black concentration, and inorganic filler loading. Data acquisition and analysis software controls all aspects of the experiment, including furnace programming, gas flow regulation, data collection, kinetic calculations, derivative curve generation, and advanced interpretation of thermal events. TGA Calibration and Verification. Accurate T/G measurements depend on proper calibration of both mass and temperature. Mass calibration is typically performed according to ASTME 2040 using certified reference weights traceable to national standards. The objective is to establish a reliable relationship between actual sample mass and the signal generated by the balance. Temperature calibration is equally important and is commonly performed according to ASTME 1582. Calibration may be achieved using either melting point standards or magnetic transition standards. While melting standards such as indium, tin, and zinc are sometimes employed, Curie point calibration using magnetic materials is often preferred. In this method, the temperature at which a magnetic material loses its ferromagnetic properties is compared with its certified Curie temperature. Several factors influence temperature calibration accuracy. These include the type of purge gas, gas flow rate, heating rate, sample pan geometry, and sample mass. For example, helium possesses a significantly higher thermal conductivity than nitrogen, resulting in differences in heat transfer characteristics and apparent decomposition temperatures. Calcium oxalate is frequently used as an internal performance verification material because it exhibits highly reproducible and well-defined decomposition steps. Although not considered a certified reference standard, repeated calcium oxalate analyses provide valuable information regarding instrument consistency and operator performance. Baseline verification. Before analyzing actual samples, it is good laboratory practice to perform a baseline verification experiment using an empty sample pan. During this procedure, the pan is subjected to the same heating program and atmosphere intended for the actual experiment. The resulting baseline provides information about balance stability, buoyancy effects, and thermal drift. Baseline verification is particularly important when measuring small weight losses associated with residual solvents, adsorbed moisture, or trace volatile components. A properly functioning instrument should exhibit minimal baseline drift, typically less than plus or minus 10 micrograms over the experimental temperature range. Sample pans and crucibles. The selection of an appropriate sample pan or crucible can significantly influence experimental results. Platinum pans are among the most commonly used because they exhibit excellent thermal conductivity, chemical inertness, and ease of cleaning. They are suitable for most polymers, pharmaceuticals, and organic materials. However, platinum can alloy with certain metals at elevated temperatures and should therefore be used with caution for metallic samples. Alumina or ceramic crucibles are preferred for corrosive materials, inorganic compounds, minerals, and catalysts. These crucibles offer excellent chemical resistance and can accommodate relatively large sample sizes. Their porous nature, however, may increase the likelihood of contamination and complicate cleaning procedures. Disposable aluminum pans provide a cost-effective option for routine low-temperature analyses. Their use is generally limited to temperatures below approximately 600 degrees Celsius, because aluminum itself begins to soften and degrade at higher temperatures. Sample preparation guidelines. Careful sample preparation is essential for obtaining reliable and reproducible TGA data. For most routine analyses, sample masses between 10 and 20 milligrams provide an optimal balance between sensitivity and thermal uniformity. Larger samples ranging from 50 to 100 milligrams may be used when measuring volatile content or determining very small residual masses. Particle size also plays a critical role. Samples should be finely divided and uniformly distributed within the pan to promote efficient heat transfer and minimize temperature gradients. Large particles or agglomerates can produce broadened decomposition peaks and inaccurate results. Uniform sample placement within the pan is equally important. The material should form a thin, even layer covering the pan bottom rather than being piled into a thick mass. Uneven sample geometry can alter heat transfer characteristics and shift observed decomposition temperatures. Moisture-sensitive materials should be stored in desiccators and handled carefully to prevent adsorption of atmospheric water before analysis. This precaution is particularly important for hygroscopic materials such as polyamides, cellulose, and silica-based nanomaterials. Purge Gas Selection. The gaseous atmosphere surrounding the sample profoundly influences thermal behavior and decomposition pathways. Nitrogen is the most widely used purge gas because it is inexpensive, readily available, and provides an inert environment suitable for pyrolysis and decomposition studies. Helium is also inert, but possesses significantly higher thermal conductivity, making it particularly useful in TGA-MS experiments where efficient transfer of evolved gases is desirable. Argon is employed when complete inertness is required and when interactions between nitrogen and the sample are possible. In contrast, air and oxygen are used when studying oxidative stability, combustion processes, or oxidation kinetics. In some cases, oxidative atmospheres improve the resolution of thermal events by promoting complete combustion of organic components. Many advanced TGA experiments employ gas-switching protocols. For example, a polymer composite may initially be heated under nitrogen to decompose organic constituents and subsequently exposed to air at higher temperatures to combust residual carbonaceous materials. Such approaches enable accurate determination of polymer content, carbon black concentration, and inorganic filler loading. Conducting a typical TGA experiment. A typical TGA experiment begins with tearing a clean sample pan and loading a carefully weighed sample, usually between 10 and 15 milligrams. The instrument is then purged with the selected gas, often nitrogen, at a flow rate of approximately 50 to 60 milliliters per minute. A heating program is established, commonly involving heating from room temperature to 800 degrees Celsius at a rate of 10 degrees Celsius per minute. As the sample is heated, mass changes are continuously recorded. The resulting thermogram and DTG curve reveal information regarding moisture content, decomposition temperatures, and residual inorganic content. If filler analysis is required, the atmosphere may be switched from nitrogen to air at elevated temperatures to combust carbonaceous residues. For example, a polypropylene composite containing calcium carbonate filler may exhibit an initial moisture loss below 120 degrees Celsius. Polymer degradation between approximately 300 and 500 degrees Celsius, carbonate decomposition near 700 degrees Celsius, and a final inorganic residue corresponding to calcium oxide. Interpretation of TGA data. Interpretation of TGA data begins with identifying the nature and sequence of mass changes observed in the thermogram. Initial low-temperature weight losses are frequently associated with removal of adsorbed moisture, residual solvents, or physically bound gases. For instance, silica nanoparticles often exhibit measurable moisture loss below 150 degrees Celsius due to their high surface area. Multiple stepwise weight losses generally indicate distinct decomposition processes occurring at different temperatures. Polyvinyl chloride provides a classic example exhibiting an initial dehydrochlorination stage followed by degradation of the remaining carbonaceous backbone. Weight gain is less common, but can occur when materials undergo oxidation. Metallic powders, for example, frequently gain mass during heating in air because oxygen is incorporated into the sample to form metal oxides. The residual mass remaining after completion of the experiment often represents inorganic components such as fillers, ash, ceramics, or metal oxides. This information is particularly valuable for compositional analysis of composites and filled polymer systems. Applications in materials characterization. Inorganic materials. TGA is extensively employed to investigate dehydration of hydrates, decomposition of carbonates, oxidation kinetics, catalyst activation processes, and thermal behavior of minerals. A classic example is calcium carbonate, which undergoes decomposition between approximately 700 and 900 degrees Celsius to produce calcium oxide and carbon dioxide. The observed mass loss corresponds directly to the release of carbon dioxide and allows quantitative determination of carbonate content. Organic materials. In organic chemistry and pharmaceutical research, TGA is used to determine residual solvent content, assess drug stability, investigate decomposition pathways, and identify polymeric materials. The technique is particularly valuable for quality control applications where moisture and volatile content must be carefully monitored. Nanomaterials. Nanomaterials often possess large surface areas and complex surface chemistries. TGA provides a convenient method for quantifying surface functional groups, organic coatings, ligand loadings, and adsorbed species. Functionalized carbon nanotubes, graphene derivatives, and nanoparticle systems are routinely characterized using this approach. Plastics and polymer composites. Among all applications, plastics and polymer composites represent perhaps the largest area of TGA utilization. The technique is routinely used to evaluate thermal stability, determine filler content, assess oxidative resistance, and predict long-term performance. Because different formulation components decompose within characteristic temperature ranges, TGA often allows quantitative determination of polymers, plasticizers, carbon black, flame retardants, and mineral fillers within a single experiment. Thermal degradation and stability of common polymers. Polyethylene exhibits excellent thermal stability up to approximately 290 degrees Celsius. Above this temperature, molecular weight decreases due to chain scission, while rapid volatilization becomes significant beyond approximately 360 degrees Celsius. Oxidative degradation is influenced by chain branching because tertiary carbon atoms are more susceptible to radical attack. Polypropylene begins to degrade near 230 degrees Celsius through random chain scission reactions. Compared with polyethylene, polypropylene is considerably more vulnerable to oxidative degradation due to the presence of tertiary carbon centers along the polymer backbone. Polystyrene exhibits degradation behavior characteristic of random scission mechanisms. Thermal decomposition generates substantial quantities of styrene monomer along with smaller amounts of oligomeric products. The rapid decrease in molecular weight and distinct DTG peak make polystyrene readily identifiable by TGA. Polyvinyl chloride is among the least thermally stable commodity plastics. Its degradation begins with dehydrochlorination, during which hydrogen chloride is released and conjugated polyene sequences are formed. This process is accompanied by discoloration, embrittlement, and eventual breakdown of the remaining carbonaceous structure. Polyacrylonitrile undergoes cyclization and formation of conjugated carbon-nitrogen structures at relatively low temperatures. These reactions are critical in the manufacture of carbon fiber precursors and are accompanied by progressive color changes from yellow to red and eventually black. Polytetrafluoroethylene is one of the most thermally stable commercial polymers. Decomposition generally occurs above 500 degrees Celsius and proceeds primarily through depolymerization to tetrafluoroethylene monomer. Polyamides are particularly sensitive to residual moisture, which can initiate hydrolysis of amide linkages during thermal processing. Degradation commonly generates water, carbon dioxide, and other volatile products, making moisture control essential during polymer processing operations. Kinetic analysis and lifetime prediction. Beyond simple compositional analysis, TGA provides valuable information regarding degradation kinetics. By performing experiments at multiple heating rates, parameters such as activation energy, reaction order, and rate constants can be determined using methods including Kissinger, Ozawa, Flynn-Wall, and Friedman analyses. These kinetic parameters enable prediction of service lifetimes, storage stability, processing windows, and thermal aging behavior. Consequently, TGA has become an important tool for reliability assessment of engineering plastics, electronic materials, coatings, adhesives, and high-performance composites. Hyphenated TGA techniques and evolved gas analysis. Although TGA provides highly accurate quantitative information regarding mass changes, it does not directly identify evolved gases. To address this limitation, TGA is frequently coupled with complementary analytical techniques. TGA-FTIR. Thermogravimetric analysis coupled with Fourier transform. Infrared spectroscopy enables real-time identification of gaseous decomposition products through their characteristic infrared absorption spectra. For example, degradation of polycarbonate can be monitored through detection of bisphenol A and other decomposition products evolved during heating. TGA-MS. Thermogravimetric analysis coupled with mass spectrometry provides molecular weight and fragmentation information for evolved species. This technique is particularly useful for studying polymer pyrolysis, catalyst reactions, fuel decomposition, and advanced materials. TGA-GC/MS. When coupled with gas chromatography and mass spectrometry, TGA becomes a powerful tool for separating and identifying complex mixtures of evolved gases. This approach is widely employed in plastics recycling research, biomass conversion studies, and fuel characterization. Evolved gas analysis, EGA. Evolved gas analysis represents a family of techniques designed to determine not only how much mass is lost during decomposition, but also the chemical identity of the evolved species. Water, carbon dioxide, carbon monoxide, ammonia, hydrogen chloride, hydrocarbons, and numerous organic fragments can be identified and correlated directly with specific weight loss events observed in the thermogram. Such information greatly enhances interpretation of degradation mechanisms and reaction pathways. Conclusion. Thermogravimetric analysis is a versatile and powerful thermal characterization technique that provides quantitative insight into thermal stability, composition, degradation, behavior, oxidation resistance, moisture content, filler concentration, and reaction kinetics. Reliable results depend on careful calibration, appropriate pan selection, proper sample preparation, and suitable control of purge gas conditions. TGA has become indispensable for characterization of inorganic materials, polymers, plastics, composites, pharmaceuticals, catalysts, fuels, and nanomaterials. When combined with spectroscopic and mass spectrometric methods for evolved gas analysis, TGA offers unparalleled insight into thermal decomposition mechanisms and remains one of the most important analytical tools in modern materials, science, and industrial research.